Hello Pre-Calc BC. Today we will be talking about something called the numerical derivative and also how to graph derivatives with your calculator, which I'm sure will be very exciting for you. First though, we're just going to do a little more challenging of an example, but similar to what we did yesterday. So we're going to find all values of x for which the function is not differentiable, and we're also going to classify, it doesn't say, but we're going to classify why the function is not differentiable at that location. So the first thing we're going to do is we're actually going to graph this. And we'll take a look at it. Alright, so it looks like this. So clearly, from the visual, you might have an idea of whether we're dealing with a cusp, a corner, or a vertical tangent at this point. You can notice that there's definitely a turning point here in which we're going to have an issue. Another way to determine what that turning point is without your calculator is just to pull out the 4 here. Okay, and so what this actually means is that the turning point is occurring at 2, 6. That is this location right here. Okay, so if you didn't have your calculator, you could figure that out by just factoring there. So the location where we're not going to have differentiability is going to be at x equals 2. But now we have to prove why that's the case. Okay, so what I'm going to do is use my alternate definition. I'm going to say limit as x approaches 2 from the left. That'll be f of x minus f of 2 all over x minus 2. So that's this guy minus, oops, I forgot my limit notation. Try that again. So f of x minus f of a is plugging in a 2 for that, but you're just going to get 6, right? 4 times 2 is 8 minus 8. Okay, so I'm just putting 6 all over x minus 2. Okay, keep on trucking. Oh, and I also wrote this wrong. Gosh, guys, I'm struggling. That plus 6 is outside of the cube root, which actually makes our life easier, right? Because then those 6's are going to cancel. Alright, so now what we're going to do is we are going to write this a little differently. Like I said, this one is kind of a special case. It's a little more challenging than you're normally going to see. So this, we can rewrite this as multiplication. The cube root of 4 times, I'm going to write it as x minus 2 to the 1/3 power. You'll see why in a minute. You could write it as 4 to the 1/3 power as well, but the key thing here is I want you to notice you have an x minus 2 on the top and the bottom, and so what I can do is use laws of exponents here and subtract. That's why I'm doing this. So I have 1 minus 1/3 is x minus 2 to the 2/3 power. Okay, so now think of this, it's similar to like when we were approaching a vertical asymptote. We don't have a vertical asymptote here, but you can kind of think of it in the same sort of idea. So we're approaching 2 from the left. Okay, when you do that, it would be like a 1.99 or something like that. You're going to get a negative number in here, but then it's going to get squared, right? This 2/3 power, you're squaring it. So you will end up with a positive. The cubed root of 4 is a positive. So this is going to mean that you're approaching positive infinity. Okay, so then if we do this limit as x approaches 2 from the right, which I'm just going to bring down over here, all of this work would be exactly the same. So I'm not going to rewrite it all out again. It would just be limit as x approaches 2 from the right of the cube root of 4 over x minus 2 to the 2/3 power. Okay, so again, it's just the same thing. Now we're plugging in something just to the right of 2, so like 2.01, something like that. Well, you're still going to get a positive down here, so it's still going to be a positive over positive, and so that's going to be a positive infinity. Okay, again, you can think of it similar as when we're approaching a vertical asymptote, but this is not a vertical asymptote. This is actually a vertical tangent, because from the left and from the right, we are approaching the same thing, which is a positive infinity. So we're going to be differentiable over all x's except x equals 2. And we have a vertical tangent, and that's because our left-hand derivative and our right-hand derivative are infinity. Okay, so a cusp is when you have a positive infinity and a negative infinity. And looking at the graph really helps this, because you can see like your slope, it's going the same way, right? It's like really positive, really positive. So they're almost approaching vertical. So that's why we say infinity. Now, something that I would have shown you if you were in class, but you aren't, is a lot of people struggle with the idea of why we can take the derivative at the vertex of a parabola, but not at an absolute value curve, because I mean they're pretty similar, right? So here is a visual that I find very helpful. I'm going to zoom out a little bit. So here's an absolute value curve, and you can watch this little dot. This is the slope of the tangent line, right? And you can see it is a very abrupt switch from -1 to +1. Okay, very abrupt. You can see it's like slope of -1, that's the green, and then zoop, it switches. As opposed to if we have, I'll put it this way, a parabola, you can see it's a very gradual shift. So it's slowly become horizontal, it's horizontal, and then it's slowly becoming steeper. So that's the key difference here, is that with a corner, the switch, it isn't gradual. It is, you're going from one value to another value. That's it. Whereas with a parabola, you can see the slope of the tangent line changes very gradually. That's why we can find the derivative at the vertex here, but we can't find the derivative here. Okay, hopefully that clears up some stuff from yesterday if you had questions on that. All right, so next we're going to talk about something called the symmetric difference quotient. Basically, the symmetric difference quotient uses 2 points on opposite sides of your a value, and this provides a close approximation of the derivative that your calculator can compute. So your calculator, we know that h means elapsed time, and we can't plug in a 0 for elapsed time, so your calculator uses 0.001, which is really close to 0. Now, to give you a visual from your book as to why this is the symmetric difference quotient, the reason it's called the symmetric difference quotient is because they're using symmetry. They are taking, instead of using f of a, which is right here, which is our point of tangency, they are taking a point a minus h, which is to the left of point a, and the point a plus h, which is to the right of a. Those are symmetrical, right? Because they're h away from a in each direction. And what they're saying is when they do the difference quotient with those 2 points, they're actually getting a more accurate slope of the curve than the regular difference quotient. Okay, so the reason that they have this 2h down here, in case you're confused as where that came from, we're still doing slope, right? So it's f of a plus h minus f of a minus h. And then what they're doing is they're taking a plus h minus a minus h. And when you do that, your a's cancel and you just get the 2h. Okay? All right, so what we can do is we can use our calculator to find what's called the numerical derivative of f at point A. And this is at a specific a value, and this is just if you don't have a specific a value. So here's the thing, your calculator can actually do this all for you. You don't even have to use this formula, but we're going to use it like once or twice to say that we did. And then I'm going to show you how to use your calculator. So your calculator is going to use Math 8. So hold your horses, we'll get to that in a second. So if you're being asked for the numerical derivative by hand and with your calculator of f of x equals x cubed when x is 2. So here's how you would do that. We're going to actually do this 3 ways. Whoa. All right, so we're going to take f of a plus 0.001 minus f of a minus 0.001 all over 0.002. And notice you do not need limit notation for this because we're plugging all these numbers in all at the same time. Oh, and this 0.002 is again because h is 0.001, so it's 2h. Okay, so now I am plugging in a 2, so 2 plus 0.001 and 2 minus 0.001 all over 0.002, and then again, okay, sorry about that, had a couple technical difficulties there. So, alright, 2 plus 0.001 cubed minus 2 minus 0.001 cubed all over 0.002, so I've already typed that into your calculator for you. And divided, and I get a 12.000001. Or essentially a 12, right? Okay, I'm just putting 12. So, now, that was fun and everything, but let me show you how to do that with your calculator. So you're going to go to Math 8, which is n deriv here, and we're going to do d dx. That means we're taking the derivative with respect to x, and x is our variable, so that's why we're doing that. And then we'll type in our function, so that's x cubed. So I'm taking the derivative of x cubed, and I'm taking it where x is 2. Ta-da! And you get the same thing. It's very exciting. So that's n deriv. That's what your book refers to it as. So that's d dx of x cubed where x equals 2. And we also got 12. Okay, so now we're going to do this using difference quotient, or we can go ahead and do the alternate definition of derivative. I just want to show you how to do that. Okay, so I'm going to do the limit as h approaches 0 of f of x plus h minus f of x all over h. And so that's going to be f of 2 plus h minus f of 2 all over h. Okay, and then we're plugging in 2 plus h cubed. Oops. 2 plus h cubed minus 2 cubed is 8 all over h. Okay, don't worry, I'm going to FOIL for you. Okay, so there I filled it out for you. H cubed plus 6h squared plus 12h plus 8 minus 8 all over h. 8's cancel. I'm going to pull out an h. Whoops, I need an h squared. Okay, h's cancel. I have this. And when I plug in a 0, I get 12. Look at that. Okay, very exciting. So now, you're probably wondering, why can't I use this all the time? Besides the fact we want you to be able to do this non-calculator. Well, that's because n deriv cannot be used to find the derivative at a cusp, corner, etc. Your calculator does not have a brain. It does not know the difference. So you need to know if the function is differentiable at that point before you can use your calculator. Okay, so for example, we're going to find the derivative of y equals absolute value of x at x equals 0 using your calculator. Then I'm going to show you how to graph the function and its derivative. So here's the thing. You should already know, because we just talked about it a couple minutes ago, that we can't find the derivative of y equals absolute value x at x equals 0. And that's because our right-hand derivative is a 1, and our left-hand derivative is a negative 1, right? So we call this a corner. Okay, not differentiable at x equals 0. Left-hand derivative is not equal to the right-hand derivative, so we have a corner. Okay. However, when you use your calculator, Math 8, d dx, whoops, absolute value of x, and we're doing where x is 0, it gives you that. Let me just write that down. So, why did it do that? They're using the symmetric difference quotient. So what they're doing is they're saying, okay, just to the left of 0 is here, just to the right of 0 is here, and they're taking the slope of that. So that's a horizontal line, so they're saying the slope is 0. Okay, but it's not. So you need to know that there's a corner there and that the derivative does not exist. Okay, so let's look at how we would graph this with our calculator. You go to your y equals, type in your original function, so absolute value of x. That gives you this guy. So then you can also graph and derive. So go ahead and do your Math 8, d dx. And what I do, you can put absolute value of x if you want, but what I do is I just put y1, and that way when I leave this in here, it'll always find the derivative of whatever's in y1. So I'll go to vars, y-vars, function y1, and we want it to graph the derivative over all x's, not just at a specific point, so you're going to say x equals x. Okay, so the blue is the original function and the red is the graph of the derivative. All right, cool. Go ahead and draw that. Did it work? Okay. And let's talk about what that actually means. Oops. So, basically what this is telling you is that as x is greater than 0, your slope is constant at a positive 1, and as x is less than 0 of the function, the slope is constant at negative 1. So here m equals positive 1, here m equals negative 1. So again, notice when the slope is positive 1, the graph of the derivative, the y-coordinate is up at positive 1. And when the slope is negative 1, the graph of the derivative is down here at negative 1. All right, so it says, what does it look like? Analyze the graphs. So I'm just going to write that in words here. I'm going to say when x is greater than 0 on the function, the slope is constant at 1. This means the y-coordinate of the derivative is constant at 1. And when x is less than 0 on the function, the slope is constant at negative 1. And this means the y-coordinate of the derivative, of the graph of the derivative, I should say. Is constant at -1. This is a lot of writing. All right, so now we're going to do that with two other graphs. Hooray! Graph the function f of x equals natural log of x and its derivative using your calculator. What does it look like? Analyze the graphs. Okay, so again, the benefit of using this d dx of y1 is that you don't have to change that one at all. We're just going to type in natural log of x. And the blue is the original function, and the red is the derivative. I'm going to bring that over here. You can go ahead and graph it. All right, so let's look at this one more time. The blue was natural log of x. And the red is the graph of the derivative, so that's f prime of x. All right, so here's what we want you to notice about the graph of the function versus the graph of the derivative. What you should notice is that the graph of f starts out very steep, but with a positive slope, right? This is going uphill. But then m starts to approach 0 because your graph kind of becomes more horizontal. Okay, so I'm going to write that first. The graph of f starts very steep with a positive slope and then m begins to approach 0. Okay, so now what does that mean about your derivative? So notice the graph of f starts very steep with a positive slope. So that means that f prime is in the positives. See, the y-coordinates are in the positives. And then m begins to approach 0. So that's why f prime begins to approach the x-axis. Okay, it's approaching a y-coordinate of 0. So I'm going to say, therefore, the graph of the derivative, or I'm just going to say the graph of f prime because that's faster to write, is always in the positives. That's referring to the y-coordinate. And then begins to approach the x-axis. Cool. All right, so it also asks, what does it look like? So, I mean, yeah, we drew the graph. That's what it looks like. But look at that red function. What does it look like? Like what? It should look like a graph you're familiar with. Okay, so it is part of the reciprocal function. So this is something we're going to actually talk about in chapter 4. But what you're going to learn is that the derivative, d dx, of natural log of x is equal to 1 over x, but only where x is 0. So that's something you'll have to memorize in the future. The derivative of natural log of x, that's just something that we're noticing right now. Okay, let's do one more of these. I know this is time consuming, apologies. So we're going to graph the function f of x equals cosine x and the derivative using your calculator. You're going to notice I already have that. What does it look like? For what values of x is the function decreasing at the fastest rate? What rate is it decreasing at? Analyze the graphs. So again, to do that, we would just type in cosine x here. And I'm going to graph this from 0 to 2 pi. That's the window that I used. And I think I changed my y min and y max. just from -1 to 1 because we're dealing with sine and cosine. So there you go. That's how I got the visual that I have on my graph here, or on my screen. So, okay. This is going to be pi over 2 and pi and 3 pi over 2 and 2 pi. Okay. Cosine we know is our blue. And the red is f prime, and we should recognize that graph. It is a negative sine curve, right? Because it's going down first. So this is something that you are going to have to memorize at the end of this chapter, section 3.5, derivative of sine and cosine curves, is that the derivative of cosine x is negative sine x. All right, so for what values of x is the function decreasing at the fastest rate? Well, when it's decreasing at the fastest rate, what that's really referring to is the minimum of your derivative, right? Decreasing, so it's going down at the fastest rate. So that's saying like this spot here. So we can go ahead and we can find the min. Just make sure you're on the right graph. So red is the derivative. Oh, I keep going to the wrong one. Okay, enter. 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 So 1.57 comma -1. That 1.57, that's pi over 2. And then -1. So what that's saying is at x equals pi over 2, it is decreasing at a rate of, so since we're saying decreasing is like your negative. So it's decreasing at a rate of 1. The rate itself, or the slope itself, is -1, but since we're using that word decreasing, we're decreasing at a rate of 1. That's representing your -1. What rate is it decreasing at? Okay, so it's decreasing at a rate of 1. Okay, up here at 3 pi over 2, it would be increasing at a rate of 1. Okay. All right, so now let's analyze the graphs. Again, when you do this, you want to talk about how the graph of the original function is represented in the graph of the derivative. So I would talk about where my slope is positive, where my slope is negative, and also where my slope is 0. So I'm going to start off by saying when f has a min or a max, okay, so that's here, 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 f prime, the derivative, is equal to 0. Okay? Because again, the slope of your tangent is 0. You have a horizontal line. This means that at these x values, and in this case that's x equals 0, x equals pi, and x equals 2 pi, f prime crosses the x-axis. Okay, or you could say has x-intercepts, and you can see that that's true. Okay, the slope is 0, x-intercept. The slope is 0, x-intercept. The slope is 0, x-intercept. Okay, now let's talk about when our function is decreasing. So we're decreasing here. When f is decreasing, and that's from 0 to pi, that's an interval, the y-coordinate of f prime is in the negatives. Okay, because decreasing means a negative slope. Okay, and we can see that. Negative slope from 0 to pi. So look at this whole section here. From 0 to pi, the derivative is in the negatives. Okay. And then when f is increasing, or a positive slope, and that's going to be from pi to 2 pi, from pi to 2 pi, the y-coordinate of f prime is in the positives. Okay, and again, we can see that. Positive slope from pi to 2 pi, f prime is in the positives. Okay, so basically it's important that you are able to describe that when the slope of your original function is positive, that means that the graph of your derivative, the y-coordinates will be in the positives. And when the slope of your function is negative, that means the y-coordinate of your derivative will be in the negatives. And when the slope of your original function is 0, meaning at a min or a max, that's representing the x-intercepts of your derivative. Okay, hopefully this has helped. I hope you have a great rest of your day.